Okay, another shocker today. I'm going to talk about black holes. Everybody's talking about them. And what is a black hole? And before you can even possibly understand what a black hole is, you have to understand what black matter is versus white matter. Well, black matter is what they call muons, bosons. There's a bunch of different names they come up with now. But it's a particle that CERN has seen, and it's just a black ball. And it goes on its own way, and when it concusses into a different medium, so it's coming at it like, say, a high speed, high voltage. When it hits that medium, nothing happens to it. When the electron portion, the glowy white portion hits, it forces all other electrons out of its way. And that's because it is a pusher. This is a puller. And I'm going to show you them right down below here, right there. Here they are. There's the pusher. The white ones, they cause electron showers, exactly what you see there. Look, let's just look in its totality. You see the black balls? Those are the muons. You say, well, no, they're not. They're just black things there. They have nothing to do with the electron showers. Oh, yeah? I'm going to show you where they came from. They came into this venturi attached in a 4-banger box. And here's what they looked like when they came in. Just before they concussed at the venturi, this was their configuration. The black balls, which are gravity, which are the muons, which are the dark matter, never seen before, were completely attached to the white matter, which is our electron. Now, so they're dipoles. There's one here and one here. Back to back, just like 2-bar magnets. Coming through the air this way, we can see this one is glowing, enhanced, because it's in the forward leading position of concussion. And they will always orient themselves to the Earth because of the magnetic attraction to the Earth. Now, you can see they're spiking here. Prior to this, you don't even see them at first. And then they start to glow a little bit, and then they concuss into this box, and then they just actually separate and go on their own way as separate particles, as I just showed you. So here it is. There's the concussion right there. There's the separate particles. And then they come back together at the end and snap back together and create these. This is a single slit. It's a venturi. I have all kinds of details. I have so many details on this. It's somewhat embarrassing. But here's how the thing happens in the beginning. Pulsation of red laser. All right. It normally is just a nice wave, and I can show that, and I have shots of that. And then the particle, which I just showed you, that little box, which creates a wave ahead of it because it's magnetic. Everything there is has a magnetic component to it. And if you push it hard enough against something else, something's going to happen. It's just the way it works. And it's called the Casimir effect. So it's a particle wave duality. So that explains that. Light accelerates its own speed, so there's no speed of light. If you can accelerate light, that means, forget about Einstein, there's no way you can justify that. You could justify a cessation of the exact speed of light, which there's no question we slow down the speed of light. However, because whatever media it's traveling through. Now, Einstein talks about a vacuum. It doesn't matter. Vacuum, non-vacuum, if I can accelerate it, the vacuum has nothing to do with it. Now, what are we looking at here? We're looking at atomic explosion right here. That's atomic fission. And oh, come on, Roger. Well, you just saw the black particle go away from the white particle. They were one particle back here. They have fissioned there, and the extreme radiation here it shows that the increased energetic value. Think of it now. Clear your mind. The increase of this energetic value from there to here is just staggering. And they claim it's 200 times. Let's go with that. That means if you could use 50 of those times to come back here and make this thing keep working, you got 150 of them you could go do something else with. Now, and all it is push to shove, because that's all any energetic reaction is. I don't care what it is. If it's burning, if it's chemical, if it's friction, it doesn't matter. It's a push of one electron to another. Sometimes they push because they're literally being scrubbed against and you can feel the heat. Sometimes they're pushed because of electrical, batteries and, motors and stators and all that business. Yes. But it's always, always, always something pushing another electron. There is no other reactions that do anything. And if chemistry can release electrons because of bonding and moving electrons on, and they get released. Just like you ever do concrete? You make concrete, it gets hotter than hell. And that is the chemical reaction of bonding things, and then it has to release that energy. It's not this hard to understand once you can step back and think about it as these dipoles. Nobody's ever considered light to be a dipole. Nobody's ever considered the dark matter to be stuck to the white matter. And the reason the dark matter has so many extra dark particles, because we can see they separate. There's no question they can separate. That case is closed. So what happens, the white ones, they don't want to be anywhere near each other. The black ones couldn't care less. They'll just lay right on top of each other. So these will push to the farthest they can, the white ones. And the dark ones will fill in all of the little places where they don't want anybody next to them. So I could see it being 85% of the universe. They just fill in the holes. Okay, I guess the best way to just do this is do it. That is a black hole, and that's in space. And the reason that black hole is there is because all of these particles are charged particles, and they are in a container which also has charges that push those charged particles in, and the dark matter can literally separate from the white matter. We've done it with experiments right here on Earth. We could never do this on Earth. The only way you can do this is in a vacuum in zero gravity, and that's what they did, and that's a black hole. And that's dark matter. And as far as I'm concerned, the case is closed. I'm going to show you all of the details that prove this. Now, before I go forward here, I just want to explain to you what they had expected when they put this dust in here with all this, this very, very, very fine dust. And it has extra electrons, they're charged particles, plasma. So when it entered in here, they literally came in like lined up streams. You should watch this whole thing. It's like 10 minutes long. But anyway, they came in streams like this and forcing down to a point. I understand, because the electrons that are around surrounding the framework here. Let's go to this one here. This is my interpretation of what they're seeing. They shot them into here. And when they went in first, they went in like a bullet like this, and then they went all crazy. And then all the black stuff went right to the center, and all the white stuff, just what you can see here. Now, why did that happen? They freaked out on Earth. They went crazy. One guy locked himself in his room for 3 weeks. This is micron-sized plasma. These little bits are all in here. Well, when they have a dark side to them, the dark side can just separate. They just completely walk away. It's just amazing. And the dark ones don't have any problem being right on top of each other. The white ones, forget about it. That's why the white ones want to be so far away from each other that they push all their black ones into the center. And they always coat everything. 100% of everything there is coated with electrons. But right on the other side of the electrons is the dark matter. So we always, always, always see the light side of this, because, well, I don't show it in the ball here, but I got, I'll show it later. We always, always, always see the glowy part of everything. When there's no light hitting it, it doesn't reflect anything, so it just sits there, but we still have electrons on the outside of it. And if you took anything whatsoever and banged into that, anything to anything, will create a bounce. It's called the Casimir effect, and it's because an electron pushes another electron, boom. And when it does, it glows. That's why they're all glowing, because that's push to shove. The more push, the more shove, the more glow. The more glow, the more heat, the more radiation. This only radiates because it's being crushed like a can being crushed. They're in there and they have no place to go. So they're concussing on their own crushness. Just like if you heat up a can of soup and it's got no way to expand, pow. Well, same thing's going on here. Now, in space, it's a different story why the black holes occur. They're spinning. But that means these particles that are all attached here are scrubbing through all the other particles that are in space, because space is loaded with particles. They're not in a container like this, where there's nothing you can do whatsoever. It's completely packed in. But they cannot get out of the way of the scrub. So that's what happens in black holes, just increase more and more scrub. Now, sometimes they may go into a wide open space. Like if you look at the galaxy, you'll see arms are really white and bright. There's a lot of material there. There's a lot of scrub. But you see black hole areas where black lines, you know, there's not as many particles there. Now, if we were actually just accidentally fall into one of those places, maybe it would take away some of the heat. But if we hit a harder spot, which is more and more scrub, we're going to be hotter and hotter and hotter. All right, that's pretty deep, I guess, but it's true. Okay, my friends, this is going to be really interesting, I hope, and it is for me. They're getting deep into dark matter, black holes, all of these different things, and they say right now, this is Physics Girl, astronomers have seen light from behind a black hole for the first time. She explains it to her editors, and they go on and so forth. Now, let's just see what she has to say, and I'm going to show what I have to say about what she has to say.
Have you seen any of the headlines yet? Stanford astrophysicists report first detection of light from behind a black hole.
All right. What?
For the first time.
All right. Let me just show you why. I could show you the exact same thing here. When light spins, everybody would say, oh, light spins. Yes, it does. Now, as it spins, well, actually it's the particle that spins dragging the light around with it. See it dragging it around? So the brighter the light, that's where it's coming from, behind. You see how it's real bright here and less here? Well, I can show you that in our experiments. All right, the first thing you have to understand is light spins. This is a single slit. The light is spinning through there, coming through, and because it's charged particles, they keep this one away, this one away. They boop, 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 and that's why you get these, what they call interference patterns. But you can see there's a drill bit pattern here. It's as it's screwing its way through the slit. Now, I didn't do these experiments. Rod Warren did them, and now I'm working with his nephew. I'm telling you, it runs in the blood. They seem to like doing this. It's really working for me, I can tell you that. But this is a pulse of red laser, and that is a behind leaving pulse, I believed, ahead of it. It's all I can do is assume these things from what I'm seeing and from my years of doing this, and I mean many years now. Now, I can see it spinning this way. I just showed you that light spins. That's the spin. Now, this is the most radiant area, and this is the most radiant area as it spins around this way. These particles are literally leaving and going that way. That's why they're much darker. They're spinning, and then now they're coming back around this way and concussing into whatever is in front of it and bashing into it and making it glow. Anytime you have push to shove, you have glow. This is the pinch of the Venturi. Somewhere in here. Now, again, Rod's doing this work, so I believe there's a, you know, you can't see some of these things. And you should see the ones his nephew sent me. Man, I'm telling you, it's got my mind cooking. But you can see the particles. You see them coming down, pip, 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 and it's being crushed, and then they're turning extremely reactive. And then they're settling back down, and there they are. All right, it sounded a little crass. It's not simple, just as simple as making some transition metals and laying them out in thin films, although that is basically the process, because every one of them has a different energy value. Now, and you put a thin film, and then maybe even copper, and then another thin film, something like that. And then the energy that hits it will penetrate these layers and be absorbed by the other layers that have these specific values of distance that can absorb them. It's basically as simple as that. When you turn on your microwave, it shakes the water molecules exactly at a frequency that makes them separate or makes them evaporate basically instantly, and that gives off a ton of heat from the vibration. So what we want to do is do a similar sort of thing, only we want it to absorb those electrons and take them down to where they can be used. That's all it is. And you know, there's a lot of people that are very, very talented at this. This is not my area. I'm just saying there is a way to harvest this. They're using solar cells. I mean, this is not rocket science. Rocket science isn't even rocket science. It just kills me because they're still thinking that this space is a vacuum. It's very distressing. Okay, Roger once again, Mudfossil University, accelerating light from a red laser, increasing its energetic value from just a little puppy value into monstrous bulldog value over here, approximately a 200-time increase. I've shown this is a particle many, many times. I show here at the Venturi, the particles literally separate from the black particle and the white showers. That is the Cherenkov effect of a muon and an electron neutrino impacting, and that's what they do when they impact. Now, let's just go a little deeper, because people say, oh, big deal, so what? What's that got to do with anything? So what if we could harvest this energy? And they say, oh yeah, how are you going to do that? Well, let's think about it. Now, we can use different lasers, different colors of light, sunlight, everything. Because if you increase, you know, what you need to do is focus it first of all, and then put it into a Venturi. And the other side of the Venturi, you get this effect. There's not a physicist on the face of the planet will say that, well, it was exactly the same energy here as it was here. It was the same particle, or it's bits and pieces of the same particle, but they have nowhere near the same energy values. This is extremely energetic at this point because it has been highly accelerated, which means whatever it hits now is not like just tapping it. It's one of those things. Totally different situation. And they absolutely want to be back together. These black balls are just attractive as can be. Look at them. Zip, zip. And that's what creates these interference patterns. Single slit, once again. So we know, no question whatsoever, the black dark matter can disassociate from the white particle. I would have never expected it, so I didn't make any of this prediction. So it has a hell of a big consequence, though, because if we can increase the value of the particle from a 1 to a 200, that's a hell of an increase. And that is, I mean, virtually free energy. There's almost no moving parts here. And it's totally simple. You say, oh, yeah, all right, we'll get back to how you're going to harvest the energy. We have to make a collector plate. You say, well, what that would look like? Well, it would have to be made of what is called thin film. Now, here's the deal. Every atom has a nucleus. I can agree with that. The nucleus, however, is not 1 or 2 or 10 or 50 different protons. Every proton in my nucleus has 1,839 electrons. All right, so what does that mean? That means everything's a dipole. It means that your nucleus is going to have a positive and a negative charge. All we ever saw was what we considered was a positive charge attracting electrons in their orbits. It wasn't attracting them. It was attracting, but it was repelling them. And here's the reason. The dark matter is so much more attractive than a white, that it forms a mass in the center, and it will pull more and more whites towards it, but the surrounding whites around that mass, which is the center, say, no, we got plenty of them out here. You guys are going to have to stay away. And say, well, we want to come in because the black part is pulling at us red parts. And it says, I don't care. I told you we have enough here, which means a stable atom. So it says you can stay out there at 5 angstrom units. I don't care about that. I push you out there, you try to pull in, you stay 5 angstrom units, everybody's good. And we will become whatever we are, hydrogen or whatever it is. Now, here's the deal though. Every single orbital level, there's going to be all these levels of distance that these electrons are allowed to reside. And they will be allowed to reside there strictly because of how many are in the core and how many surround the core and how pushy and pulley they are to each other. It's as simple as that. So this guy says, no, we got enough electrons in here, enough of the glowy ones in here, so you're going to have to stay out there, way out there. And he said, well, all right, I will. And it stays way out there, so it doesn't have much of an attraction. So when that one takes off, it just sort of slips away. When they're down here and they take off, they are powerful. So what do you have to do? We have to harvest them from every one of these reaction zones. How do you do that? Thin film. In other words, one layer of electrons. Basically, the thickness of one layer of whatever the transition metals are. And here's what causes these colors. These are transition metals. And that's why you see the different colors, is because of the bounciness, literally the bounciness of these metals. How hard are they going to bounce away the electrons that bash into them? They have a whole batch of extra electrons or not extra electrons, something like that. Just think of it that way. And so they will hit and bounce, and some of them will hit and sort of keep them and give back just a little bit of them. And then you'll see it a different color. Now, we need to collect every electron that we can get that is being forced into this material and through these films. So now, once they hit the film, if they can conduct through the film, they'll just go over to the conduction plate, and you have to have set up a polarity there, and so it'll absorb them and take them down into your battery, which will want those, and or whatever device that you're trying to drive. But it's really not all that complicated. It just needs a little work, and everything there is made of is an electron. One of those. Electrons will burn you and kill you and electrocute you. They will conduct. They'll be static. They'll be lightning. They'll be discharges. Photons, a little bit different. They're sort of a semi-stable particle already, so they basically bounce off you. If you get hit enough with them at the same time, there's just going to be so much interaction that you're going to burn a little bit. But these babies, they'll kill you. And mass is literally, only thing mass is impact value. So mass is determined on a lot of things. And I have a whole set of series of things that contribute to what the mass actually ends up being. Because it's spin, and it's, whatever the particle's made of, because, not everything's just an electron. So anyway, we'll get deep into this as we go along. The school is going to just teach all of this stuff. It's all new now. And we have, everybody's going to be contributing, which is what we did right now. Nobody's getting paid. Nobody's got any money. So it's one of these things, you do what you can do with what you got. And we're doing pretty good with what we got. I'm surprised, man. I got people all over the world contributing now. I call them my informants. Because most of them don't want to be known. I'm not kidding you. It's a very, very strange world we live in now. Okay, I'm going to leave it with this. I think I mentioned Dylan Carpenter, who is Rod's nephew. This is a moon. This is with a Samsung, I think it says 820 phone, something like that. And he's just taking a picture of the moon. And then he does all kind of fancy things, rendering and this and that. I can tell you one thing. What I'm seeing right there is a dipole. It's a dipole. And that's on outer space. Now, this is obviously the moon, he said, so that's either Jupiter or a star or I don't know what. These dipoles, and everything is a dipole, are these from on the surface of the moon? Because they're in front. Or are they some kind of satellites? We don't have any stars between us and the moon, so that's kind of a shocker. I'm telling you, my life just is filled with this kind of stuff every day. Look at this. Look at this. What the hell is this all about? These obviously must be stars. But you can see they all interact with each other. They all are entangled with their fields. And this again, this big bright jobber there, I don't know what the hell that is. It could be Jupiter, I don't know. I have no idea. There's another one out here. But you see how they always have a dark and a bright side? Everything does, because everything's made from dipoles. And he did so, I don't know how he gets these fields to show up like they are. And here's, he's doing something getting real deep into the depth of the matter, because I can actually see the chip itself in here. So, and these are what they call CMOS. I believe. I better shut up about that because I don't know. But I would go with thin film receiving. That's what I would think is going on there, but who the hell knows? And that's. And this one here, look at this. There's 7 of them. 1, 2, 3, 4, 5, 6, 7. Is that the Pleiades? I don't know. That's the moon. And this is like they're just held together as a unit. I mean, it's just right now. It is. Dylan just started with me anyway. I don't know. He's been working with Rod at all, but just within the last couple of months. So we're just really starting to see a little bit of this and a little bit of that. But I can tell you what, here's your dark matter and here's your light matter over here. It's a dipole. Even every molecule is a dipole too. It's not necessarily the dipole. Let me rephrase that. Every atom, every molecule, everything has polarity to it. It's made of dipoles. Let's just stay with that. That works. And then they get pushed this way and that way depending upon their polarity densities. I guess that's the best way I can say it. It's very, very difficult to get into this realm yet. And again, I can see things that I sort of suspected, but I just never really fully understood. So, and I still don't fully understand at all. So don't give me, I don't want to give you the impression that I got a solid handle on this. I think I'm getting there. But you don't get there just one step. Oh yeah, there it is, have a nice day, go home. But that's what happened. And when they came up with Bohr, yep, everybody's got to do the same thing. Bohr said do this, Hubble said do this. All of them, right down the line. And, you know, I've just shown everything is not correct. Basically, that's basically the bottom line. Everything is not correct.